Hi, my name is Huaizheng. Today I'm going to talk about how to leverage 5G edge computing for whole body robot control. This is a joint work by me, Huaizheng Zhu, Malali Sharma, Kaifa Pfeiffer, Marco Mezzavilla, Jashan, Sandeep Rangan, and Ludwig Rigatti. Legged robots can be very useful for real-world applications, such as disaster rescue and advanced manufacturing, due to their mobility. However, to fully unlock their capabilities of reacting to the ever-changing environments, these robots have to be equipped with tremendous amount of computational resources, which is not only uneconomic, but also increases the power consumption and thus reduces the battery life. While the idea of overloading intensive computation to the cloud is nothing new, it remains elusive for latency-critical tasks, such as whole-body control of legged robots, as traditional cloud computing introduces significant delays in the control loop. Now, the fifth-generation cellular network may offer a solution to this issue with the mobile edge computing technology. How does 5G mobile edge computing differ from traditional cloud computing? In 4G LTE networks, for example, data packets are routed through a centralized gateway before they reach the cloud service, causing delays in excess of 50 milliseconds. In 5G mobile edge computing, computational resources are brought closer to the network edge, sometimes even embedded in the base station directly, to drastically reduce the delay in the core network. Meanwhile, the usage of millimeter wave bands further lowers the delays in the air link to 1 to 2 milliseconds, allowing ultra-fast communication that is within the requirement of state-of-the-art torque control methods. However, a drawback of using millimeter wave bands is that the signals can be easily blocked by common objects such as buildings, people, or other robots in the environment. This blockage effect may cause intermittent link outage, causing delays, jitter, and packet loss. Since the state-of-the-art robot whole-body controllers are very susceptible to delays, the blockage effect of millimeter wave bands is a key challenge in offloading the whole-body controllers to the network edge. In this work, we propose and study the first edge-based whole-body controller over a 5G link. Our approach provides an efficient local controller to enhance the performance of a purely remote controller on the network edge in presence of unexpected delays. To illustrate our approach, we first review the task space inverse dynamics controller. It formulates the control task as quadratic programs, where the weighted sum of deviations from the desired task space acceleration is minimized in the least square sense. Meanwhile, the solution has also to obey linear equality and inequality constraints, such as dynamics consistency, rigid contacts, approximated friction cones, and etc. The solution to this QP can be written in a matrix vector multiplication form, where the red matrix underlying a double-daggered opt is the hierarchical inverse that contains the optimal active set normals and the task Jacobians. This inverse is implicitly given when computing the solution and has a cubic time complexity. The blue vector underlying B opt contains the optimal active set biases and the error feedback terms. While it is susceptible to delays, it can be computed in linear time. This structure of the optimal solution grants us a natural partition of the computation. We can offload the full QP computation to the remote server and only maintain a cache of the red matrix, while updating at the control frequency the blue vector onboard. Altogether, our approach, termed locally assisted remote control scheme, can be summarized in this diagram. At the beginning of a control cycle T, the robot maintains a cache of the hierarchical inverse and the active set from the most recent successful communication. The robot measures its state and sends it to the remote server. Meanwhile, it constructs the vector underlying bopt from the measured states. If the robot doesn't receive the solution from the remote server at a predefined time threshold D star, then the local controller will apply the product as an approximate solution. Otherwise, the solution from the remote server will be used, and the local cache will be updated accordingly. At the next control cycle, this process repeats. It is worth pointing out that the control scheme we just described relies on the assumption that the optimal active set does not change too much in presence of delays. This assumption may be problematic for tasks that involve context switches, such as locomotion. When the robot switches from one contact mode to another, very different constraints will be introduced, and so is the case for the active set. To mitigate this problem, we found it helpful to utilize the onboard computer even though it only has a limited computational capacity. The insight here is that the local controller can help to improve the control performance whether the delay is caused by communication or computation. In particular, around contact transition, we solve the full QP not only remotely, but also locally at a lower rate. On our simulated single-core CPU at 1.2 GHz, this can be done every 5 milliseconds. Note that the local controller is still running at the control frequency, which in our case is 1 kHz. In practice, the usage of the onboard computer upper bounds the control delay, so that unexpected high communication delays during context switch will not be detrimental to the task execution. In addition, we also pre-compute the QP solution to the next contact mode on board to ensure its availability before the context switch actually occurs. To validate our approach, we conducted a series of simulated experiments. We compare our approach with purely remote control. The purely remote control scheme simply executes the most recently received command from the server in the face of delays. We conducted both balancing and walking tasks on a 37 degrees of freedom humanoid. In our experiments, the local onboard computer is simulated by restricting the CPU frequency to 1.2 GHz while keeping it 3.7 GHz for the remote controller. When simulated with constant delays, our approach consistently reduces the center of mass tracking error and the constraint violation. Moreover, our approach significantly increases the maximal tolerable delays for both tasks. In addition, we also used the open source simulator NS3 to simulate realistic 5G networks with various moving blockers. We simulated two scenarios. In the burning building scenario, the delays are lower but more frequent, caused by small moving objects. While in the smart factory scenario, the delays are intermittent but can be very high due to the larger blockers made of metal. We generated 100 delay profiles for each task scenario combination, where the initial positions of the blockers are randomized. A task execution is considered successful when the robot manages not to fall. As shown in the table, while the performance of purely remote control is comparable to our approach for the balancing task, it fails to execute the walking task in both scenarios. On the other hand, when using our approach, the robot achieves 85% success rate in the smart factory scenario and a 100% success rate in the burning building scenario. Here are some examples of the task's execution in the burning building scenario. As shown in the video, when the local controller is used, the robot reacts more robustly to the external push and recovers more quickly from the disturbance. For the walking task, purely remote controller cannot keep the robot from falling, while our approach allows the robot to walk under significant delays. In summary, we proposed the first 5G edge-based remote control algorithm. It complements a purely remote controller with a local, approximately optimal linear controller by exploiting the structure of the optimal QP solution. Simulated experiments have shown that our approach improves the control performance in presence of unexpected delays. However, our approach is not robust against unexpected contact transitions, as we need the accurate knowledge of when and how the contact modes switches. In addition, the precomputation is also not robust for highly dynamic locomotion such as running, as the robot state may change abruptly even in a short period of time. These issues are thus left for future research. Thank you for your interest in our work.